Okay, so I'm gonna copy paste the link to the presentation and Jamboard link, whiteboard link right there. So this is kind of long and it's kind of overwhelming. There's a lot of different data structures and stuff, but the main point of today is to just kind of briefly go over data structures. And even though it's data structures, I don't want to present it as talking about data structures. I want to talk about it as what functions can you, what's the purpose of doing this? And a lot of different things you can do with different data structures. And so I want to talk about the difference. One main point I want to focus on today is the distinction between data structures versus abstract data types. So if you've taken CIS 22C, that course is called like data structures and abstract data types or something. I don't remember the full course name, but abstract data types are what you can do with the data. And then data structures might be specific implementations of abstract data types. And so, for example, a list ADT, so a list of items might be a collection of items with a set order. So it might be an ordered list or something. You have a list, you have a list of items, it's in a set order. So when you have an ADT, let's say you jot down a couple things on a sheet of paper. If it has an order and it's a collection of items, then it's a list. So that shopping list would be a list. And an array might have an order. You have a block of memory, and then you have a bunch of stuff in it. So that could be a collection of items and it has a set order. So that you could define that both of those as a list, and you can use either of those as a list. So there's different implementations of the same ADTs. So that's really important. And the same data structure can be used for many different things. Good example is array. Array, you're always going to use different types of arrays, but you're always going to use array the most just because it's so versatile and you can kind of use it in different ways. So we'll be talking about that today as well. And so time complexity of common data structures. These are data structures that specific implementations. You have like arrays and strings, you have linked lists, you have binary search trees and hash maps, but they might serve different functions. And so we'll talk about the functions and we'll talk about each specific data structures and how it might relate to that a little bit, but you can refer back to this and you'll be able to find the presentation as well. So ordered versus unordered versus sorted. So you might have ordered data. So let's say you want to keep track of the relative order students were in line and you're writing down ID numbers or something, or maybe you write down their name. So you want to keep the relative order of the students intact. So you might use an ordered data structure. So maybe an array or a string could do that. So a type of an array. So maybe you fill out an array of integers with their ID numbers or something, and then that would keep the array intact. You could also use a linked list and then have a data point and then have the next data point. It'll connect to the next data point. So you can use either of those and it would keep the order intact. But if you want to keep track of students alphabetically, then you could use something that's sorted. So maybe a binary search tree would store things in sorted order, but you could also use an array, and that would be an ordered data structure, and then sort the elements. So just because you need to keep track of students alphabetically, that doesn't mean you need to use something that's sorted already. You could put it into an ordered or unordered data structure, or you could put it into an ordered data structure and then sort that as well. So it's flexible, and you really want to be flexible with data structures and how you use them. And let's say you want to keep attendance for students and you don't need the ordering. You could use an ordered or unordered data structure, but let's say you try to use let's try to use a binary search tree or something sorted already. If you're automatically sorting, then if you want to keep, it could work as well actually in this instance, but sometimes things don't work for other things. Sorry, I should think of a better example, but we'll just move through relatively quickly today. So arrays are blocks of memory. So you might have a starting memory location, and then you have basically have like a pointer to that or something like that. And then you can store things into these memory blocks, and you can access any index in constant time. It's also called random access because you can, let's say you have an array of integers. Integers might be, you might have 32-bit integers. So 32 bits divide by 8, so 4 bytes each. And so if you have a 4-byte integer, then you have the first memory location. The next thing is going to contain the information for the second number is always going to be that first memory location plus like 4 bytes. And then the second one would be the starting place will be that index number times how much memory it takes. So 2 times 4 bytes, and then ahead of that first place. So you can directly go to that memory address by doing arithmetic with the memory location. So that's why you have random access, and you can access anything in constant time because you can just do arithmetic and then go directly to that memory address. But what if you need to find a value? So you have these indices and you need to check whether a value exists and then maybe return the index value or something. Then you need to look through every one. So that would take order of n time. If you need to insert something, then if you need to insert into the middle, then you might have to allocate new memory with more space, copy and shift the elements. So if you're putting in the middle, maybe you need to put copy 2 in, and then copy your new thing in, and then copy 2 new things in. So that would take order of n time. And then there's also a concept called mutability, array string mutability. So vectors, you might disagree that you can't insert in order of n, in faster than order of n time. And that's true if you have a mutable list, mutable array, and that means you can add to the back of an array in order of in constant time, in amortized constant time. And this is a little bit complicated, so we're gonna kind of brush through this, but really quickly. But let's say you have a vector, and then this is just one implementation of an array, of a mutable array. But if you have a mutable array like a vector, then it might double its max capacity every time. And when you don't have enough space, then it'll copy all the things and do the order of n operation. But you're only doing the order of n operations every like 2 to the n times, or yeah, so it gets like very small in comparison to the larger thing. And so you have to do it less and less, and it kind of adds up that I probably didn't explain it completely correctly, but there's basically, you can add to the back, you can add a new number in amortized constant time, which means basically constant time. But if you try to add to the front of an array, or you try to add to the middle, then you have to start shifting elements, right? And then that's going to take all the elements that you're shifting. So you'd kind of say that's order of n time. That's going to be linear time. If you're going to shift elements, then the worst case scenario, you're going to shift everything over and you have to copy everything. And so that's going to take constant time or linear time. So yeah, only to the end. And what that means, okay. So stacks can insert to the top and remove from the top. So let's say you have a stack of plates, then you add another plate on top, then the first plate that you take out is going to be from the top, right? You're not going to go Jenga style, take from the middle. You're going to take from the top again. Well, let's just say you're going to do that. But think about mutable arrays. You can add to the back, and if you remove from the back, then you can actually use an array or a mutable array as a stack as well. So you want to be flexible with how you think about things. There is such thing as a stack implementation in like C++ and a library, and in Java, you can use stacks and things like that, but it's fundamentally like an abstract data type. It's a concept of what kind of things are you doing, and it's you can use different data structures to achieve that goal. So stacks, you want to insert to the top and remove from the top in a last in, first out order, where the last thing that you do, you want to do that first. So if you have a stack of plates, the last plate that you put on the top, then that's going to be the first plate that you take off that stack. So if you can achieve that, you can do that with a lot of different data structures. Queues are like waiting in line for something. You can insert to the back and remove from the front. And so let's say you know how many people are in line, then you could actually just have a block of memory, have an array, and then fill it up forwards. And if you need a queue, you could read it from the front. If you need a stack, you could read it from the back. And that would sometimes satisfy the satisfy what a stack needs and what a queue needs. So you can actually use array for a lot of these things. And as long as you know upfront how many people and things like that. So it really depends on the implementation, what you need for your problem. But you can use the same data structures for a lot of different things. And that's really important to remember. So linked lists, this is a type of data structure where you have nodes, things called nodes, and you have a head node and you have a tail node, and you point to the next area of memory. And so you have constant time access to the first one and constant time access to the last one, but you can't really access the middle ones. And you can freely add to the front and add to the back. So if you looked at arrays, you can't really add to the front. It'll take order of n time. But with linked lists, you could add to the front as well. So there's added benefit of this data structure. And the most common one you'll be using is probably DEX. And you can use these as both a stack and a queue. You can add to the front and remove from the front, add to the back, remove from the back. So you could access, you can add, that means you can satisfy either the requirements of a queue or a stack, where you insert to the back of the deck and then remove from the front, or you can insert to the front and remove from the front, or whatever. So you can do both, and you can satisfy both of those with a linked list, like a deck data structure can satisfy both of these things. You can do both of these functions of ADTs, of stacks and queues, using that data structure. So that's the distinction between abstract data types and data structures. It's probably really confusing, but hopefully you'll get better. So what if you need to keep a collection of numbers sorted? You could have an array, but every time you add a new element, you might have to allocate new memory and then add it in and then sort, and sorting would take n log n time. So that would overall take n log n time every time you try to add a new element. But instead, you could do something like a binary search tree or some kind of priority queue. And you can use a binary search tree. Binary search tree is a data structure, and then a priority queue, I would probably classify more as an abstract data type, but I'll talk about it. So binary search trees are a type of tree where there's something's connected to, there's a root node, and then all other nodes, these are kind of child nodes, and there's a parent node, and each node has at maximum 2 different children, and they also satisfy this condition where the current node is less than or equal to every node on the right. So 10, 14, 13 are all greater than 8, and then every node on the left side is going to be less than or equal to. So the current node is going to be greater than equal to every node on the left. So 8 is larger than everything on the left side. And this is satisfied at every point in the binary search tree. So let's say 3, 1 is smaller, and then 6 or 7 are all larger. So everything on the right, everything on the left. So this condition is satisfied everywhere in the binary search tree. And in CIS22C, you'll learn that worst case time complexity is going to be pretty bad if you end up with an unbalanced binary search tree. But you don't really have to worry about that for competitive programming because the implementations and standard library kind of auto balance themselves. For example, in C++, and I think Java as well, you'll usually use something called like a red-black tree or something. I don't actually know how it works, but it does auto balance itself. There are other types of trees that auto balance itself as well. And it'll still have the time complexities of find the smallest or largest element in log of n time, find a value in log of n time, and insert or remove a value in log of n time. So let's say you need to find the value, the smallest value, then you keep on going left until you hit no more nodes on the left side, and that's called a leaf node or something. But basically you can do that. The time it takes is equal to the height of the tree, and this is going to be log of n and a balanced binary tree. I'm just going to skip over that quickly. So a priority queue is something that gets the smallest or the largest element repeatedly. And the smallest element you call like a main queue. And then if you're repeatedly getting the largest element, that's called a max queue. And one implementation of that would be like a heap data structure. And another one, you could use a binary search tree as a min queue or a max queue as well. So you need to get the top element, and you need to be able to insert a new element and resort. So let's say you have a binary search tree, you add a new value, let's say 5 or something. So you go left, you go right, you go left, because 5 is smaller than 6. And then for 4, 5 is larger, so it go to 5. And then that would make it unbalanced actually. So it would kind of reorganize itself. It'll balance itself out. The tree would balance itself out. But basically, you can do that. You can add a new thing very quickly. And then to get the top element, let's say the smallest element, you could, in binary search tree, you could go like tree dot front or something. And then you could get the first one or something like that, depending on the implementation. But you could use it as a priority queue. And oftentimes, priority queues don't require you to enable access to elements other than the top. So you need to be careful about that. Sometimes you can't traverse a priority queue. You can't get the full order if you're just talking about the priority queue in general. And you can use priority queues with custom comparators in order to sort in different ways. And we have a different presentation for sorting in custom comparators. This should be pretty easy to read, and kind of it just has like a little bit code and stuff like that, like sorting from smallest to greatest, greatest to smallest, and stuff like that. And then a couple custom comparators and just sample code. So basically, it should be easy to figure out. And some of the parts on the bottom are kind of work in progress, but you don't really need to know about the most famous sorting algorithms. You just need to know when to sort, why you should sort, how to call the standard library sort function, and be able to write and use custom comparators. So those are going to be the important things in, for sorting in competitive programming. So priority queue you can combine with custom comparators. So you can compare it in a different way. So a set is something that where you can add to a set, you can remove from a set, and you can also check whether something is contained in the set. And this is a little bit, it might be hard to wrap your head around, but you can first think of it as like using an array as a set. So let's say you have a Boolean array, and the size is n, and if you know the values will be between 0 and n-1, then if you add to the set, you can change the contain of index value to true. So you can change, flip the Boolean value to true, and then you can add that to the set. Remove, you can change the contain condition to false for that specific index, for that specific number. So if you're trying to add numbers to a set, then you could do something like that and use the index value and access it that way, and check return if contain of index is true or false in order to check whether it's in the set or not. And a map is something that stores key value pairs. So this is similar to sets, except every key in the set is tied to a value. And you can add a new pair based on the key value. You can remove a pair based on the key value. And you can check whether the key value is contained in the map or not. So let's say you use an array as a map. Like the set example, if you know the values will be between 0 and n-1, the key values will be between 0 and n-1. You can store different things in the array instead of using a Boolean array. So we had a Boolean array before, but let's say you have an int array. And then, so you change the map numbers of that specific index value to the new value. So you're tying this key value, the index, to a new, there's a key value pair, and then that value will be changed, the new value in the within the map. And then let's say you want to remove it from the set, maybe you set it to 0 or something. And if you check whether something is in the map, you can check whether it's 0 or not. And this can be really good if you're doing something like time-based, that's between 0 and n-1 or something. And then you can have the time go from 1 second, 2 seconds, or 1 minute, 2 minutes or something. And you can have the time be every index. And then, so there is an example in one of the DA hack coding problems called parking, where you had to, one solution was to note down how many cars are parked at any time, any point in time. So you could map different values to every point in time, and then you could count the number of cars at every time. So you could do something like that with a map, but there are a lot of limitations to this where you might not be able to, let's say the time goes from 1 to like over 1 billion or something. You can't always create, you can't really create an array size 1 billion, things like that. You can't trivially use a negative key. So if you're mapping time, time might go to 0 to n-1, but if you have a negative key, if you're going back in time for whatever reason, if you need to map different values, if you need to use non-integer keys, if you need to store 0 as a value, maybe some of these things won't work. So in this implementation of a map, we had map numbers of n, but the default value is 0. And the way we checked whether or not a map, some key value had a number mapped to it, was to check that it had 0 or not. So that doesn't always work if you want to store 0 as a value to store with a pair. So you can't always do that. And so you might have a tree set or tree map, or a hash set or hash map. And so binary search tree, it'll save it in sorted order. So, so you insert something into a binary search tree, and that's kind of like adding to a set. And then maybe you sort pairs of numbers instead. And if you put pairs of numbers in binary search tree, then maybe you can use that as a map. So that's a tree map. It's a little bit, might be hard to understand, but let's say 3 is tied to like 5 or something. So it would store the element 3. You have 3 and you have 5, and it would store both of these things in the same place instead of and it would sort by the key value. So you can search the key value and save it as part of the binary search tree. But it's, yeah, hopefully it's not too confusing. And then hash sets and hash maps, these are a type of set and map where you get the key, you run it through a hash function, and then that's then converted to, that hash function converts it to an index number. And so you hash the key and you have the bucket and you store data into the bucket. So you have a pair, you run the key through the hash, and then you put the value into that index location. So basically it's like an array, but you're putting things in different things. And that's why you also don't have an order. You don't have a set order with a hash map, because you're running it through the hash function. You're not putting these things in order at all. So that's why it's unordered. But yeah, it's probably, this is kind of a large overview thing of how these things, what are, hopefully you had a decent introduction to how abstract data types are different from data structures. So a map might be something that stores a key value pair, and then you could satisfy that condition with a lot of different data structures, like using an array, for example. So storing a key value pair, if you use the index as the key of a pair and then store that pair, that second value, as the value within that index. So at that memory location, then you can use that as a key value pair. You can consider that like a map. So that's why it's an abstract data type. And when someone says you can use a map for that, they mean the abstract data type, and that implementation might be a specific type of map. So that's something to think about. And a lot of problems will say like, you can use a set for this, you can use a map for this. So you can pick what data structure to use as a map or a set or a priority queue or something. And it doesn't, there's not one solution. A lot of the time you can use different data structures and achieve the same optimal result or same suboptimal result. And as long as it does it in time, then it doesn't really matter for competitive programming. So I think if there's one takeaway, this is a lot of information, but if there's one takeaway, it's like, it doesn't really matter which data structure you use. It matters what functions what you're able to do with it, and if that is in time or not. So that's going to be the main thing. If anyone has any questions, so yeah. Is there anything you want to add, Jesse or Peter?
Not really.
If there's any specific thing that you want covered again. Yeah. So if there are no specific questions for now, we'll do some example problems and then talk about how you might be able to use one data structure or another one. So let's say like, so parking example from the competitive programming, the DA hack coding competition. So this guy is driving trucks and he's parked 3 of his trucks. And the time he's parked his trucks, if there's one truck parked at the car park, then he pays A per minute. And then if 2 trucks are parked, then he pays B per minute. And then if 3 trucks are parked, the dude pays C per minute. And you're given A, B, and C, as well as the time interval in between each of Luca's 3 trucks are parked, and determine how much Luca needs to pay. So let's say this has been covered in the thing already in the for the competition already, but let's say you look at this. So you have A, B, and C, and then you have truck 1, 1, 2, and 3, and then you're given the time arrived and then depart, and then you have arrived and depart and arrive, depart. And so that's going to be an input format. And so one way you can solve this problem is to have, so you have the time will always be between 1 and 100. So you can have a timeline of when the trucks will be parked, and then say truck A will be parked from like 1 to 6 or something like that, and then a different truck is parked from 3 to 5, so 3 to 5 or something, and then the third truck is parked from 2 to 8. So if you can count the values here, like all across here, whether there is one truck parked at a time, 2 trucks parked at a time, or 3 trucks parked at a time, then you can calculate the total amount it has to pay. So you can do that with an array, or you can map values and increment that value at the part of the map. So this is actually more of a map problem, even though you can use an array to store the time places. You can think of it as a map problem, because maps aren't necessarily just tree maps and hash maps, but maps can also be arrays as well. So that's why I would consider this, you could think of it as a map problem as well. And so maybe, but a really basic question for maps might be something like this. So link this and can work on it for the next few minutes or something. Does that sound okay?
Yeah, we could work on it for like maybe give them like 5 minutes to read through it and then we can discuss.
So we just work on it right now.
Yeah. So
Okay.
Someone asked, how do we use maps? Should we explain it more?
Okay. Yeah, maybe it's better to do one example first. So, right, do you want to do it or should I do it?
Yeah, you can do it.
Okay. Going to start with a basic template, and then it seems like number of participants n. Hopefully you've read the problem already. N P to win the contest, and then M, number of lines with player names and points. So the same people can score multiple times. So you have M lines underneath here. Okay. So int N PM, CN NPM, and then for int I equals 0, I less than M, I plus plus, and then let's say map of string to integer. And the way you use a map is to specify you're storing a pair, and that pair can be, you can pair up anything with another anything else. So let's say for this, we want to pair up names, which will be string values, and we want to pair that up with different scores. So it seems like you get the names, all the names first. So it seems like map M, no, map names, I guess players would work. And then for int I equals 0, I is less than players. Yeah, you get the players first. I plus plus string name, get the name, and then players. If you're using C++, you can go like players of name is equal to 0 to do a default value, or you could do something like players dot insert, and then it's really annoying, but you have to do make pair and make pair name comma 0 or something. And this is the same thing as doing the first line. So players of name is equal to 0. This would store the map, the int value into that for that name. And then for the second one, you're inserting make pair, this pair of string int, you're inserting it into the map. So it does the same thing. And so get a default value, and then the following 13 lines, so less than M, you have the name, you have the score, and you're going to input the name and the score. And so you could go players of name plus equals score, and output the names of participants who reach the minimum score. So that means that multiple people can win the same thing. And if none have won, print out no winner. So maybe bool found winner, no winner is equal to false, maybe. And then, so maps you can iterate over. So you might go pair string int p. You could do some random. I can probably do it another way. Let's do this for player string int p. So for pair p in players, which is the map, you could do something like if p dot second, which is the score, is greater than or equal to the points necessary to win, then we want the vector of string answer, and answer dot push back the name, which is the first part of man, I'm using the same, reusing the same name, player p, and then I'll call this player. Yeah, don't reuse variable names. So player dot first, player dot second greater than or equal to p, identifier
Yes,
player. Okay,
Yeah.
yeah, I mistyped. Okay. So player dot second is greater than or equal to p. So P is that point value that's necessary, and then it's stored in the map. You can iterate over the map. And you could also do something
And
like,
I think you have to do print it in the order they list the
oh,
required score. Yeah, that's
okay,
important
okay,
detail.
okay.
Yeah.
I'll put the winners in the order they reach the required score. Okay, then maybe you have to do it here then. If players of name is greater than or equal to P, and so you could add it here, right? Instead of yeah. Then, but you don't want duplicates for winners, right? So you could cheat and go like constant int infinity is equal to that, and then if you've already won, set your score to negative infinity or something. That would be like one way to ensure like that you don't get the same people winning multiple times. So that could be one way to do it. You could probably do another check as well. But maybe this would work. If players name, or you could do like, if players of name is greater than equal to P and players, or you could do like players of name minus score is less than P, right? You could have that condition. So you could do a double conditional, or you could do set it to negative infinity or something. Either of those would work. And then answer, push back, name. In fact, you could probably just say no winner equals true, false. No winner starts at true. No winner is equal to false, and then maybe just output name space wins line. So you don't have to go through that. And if, yeah, we don't need an answer array either. Let's test this. Wait. Input, input, input name score. If players of name is greater than or equal to P and players of name minus score is less than P. If no winner, CL winner. I missed something. Let's see.
Wait,
Maybe
I
no
don't
win.
think you can use CN for a string. Because
Yeah, you can, you can.
oh, you can.
Yeah. Equal to 0. What's the score? Minimum points is 1. That should be players of name is greater than
Do you really need the second condition? I mean, the second condition, the player name minus score, that thing.
Yeah, you should need
Yeah,
it.
you erased the inf thing.
You only win once, right?
All right.
Let's do the hacky.
Yeah.
Let's set it to negative infinity. Maybe that'll work. No winner, just wins, no winner.
And for no winner, you miss the exclamation mark.
Yeah, but it's basically how you use
Yeah, but
math.
the phrase in number cases too.
Let's see. John, Kelly, George. Kelly, George, Kelly 1. Name, score, name, NPM. 3 numbers and then n. N participants, P is the point. Okay, confusing.
Yeah.
Confusing. Okay. Let's do the. Yeah, confusing variable names is bad. Oh, this should work. Yeah.
And I think if you do map in C++, you're using binary tree.
Yeah. This is a
So
binary search tree. Yes.
yeah, so if you do unordered map, then you use hash table. So it's
Yes.
kind of it's a bit more faster.
But you'll see that it doesn't matter either way.
Oh, really?
Yeah, it's not gonna make. So let's say you make it unordered map, right? So this passed, and then make it unordered map, and it'll pass. So
But I mean,
yeah.
it's a bit faster because SS is constant time.
Yes. But okay, let's check.
Yeah, let's check.
First one took
Yeah.
0.11.
Oh yeah, it's faster.
Yes, but it doesn't matter.
Yeah.
Yeah.
You're right.
Yeah. Yep.
But that's like good to know thing. Because like
How do you run?
if you first time see map in C++, yeah, you kind of assume that it's hash table, but
Yeah.
it's
yeah.
actually not.
Yeah. So definitely might do like a follow-up thing with each individual language and talk about like the implementations, because yeah, it's really annoying, right? Like stack is a linked list or something and things like that. So yeah, this is competitive programming helper. It's this app, and then there's also this thing called like competitive companion. Yeah, so you can import tasks with competitive companion, and then you can run it with the VS Code CPH, competitive programming helper. This is very helpful, but yeah, you could do it manually, but it's just so much faster, right? So I'll post this code, and I'd say rule of thumb, you shouldn't need hash map for anything. Like, to be honest, hash maps are kind of overrated. That time difference shouldn't make a difference in any problem. If that makes a difference, then it's, you're not going to be able to solve it in a different language, right? Like if it's,
And also there is like additional benefit of using map over hash table here.
Yeah.
Because like map is literally ordered. So
Yeah.
if you iterate about it, you get it by like sorted manner.
Exactly.
Yeah.
So
that's
like, let's say
also
you,
good to know.
yeah, if you output like, so we have players dot back dot end, and then minus or something. This is an iterator, and then if you get yeah, if you players dot end minus what, I don't remember the function. There's no back, right? Begin. So if you want to find the smallest one, you could go
There begin.
pointer to players dot begin. What did you say?
Oh yeah, right.
R begin.
If you do that, way, you
yeah,
have to omit the like asterisk.
So R begin is a reverse iterator. Second.
You have to remove stars.
Oh yeah. You don't need it in this case. Yeah. Yep. If you're using a set, then use the star instead. maybe. Yes, use star instead. But let's say you run this, then you can get the high score. George got 10, Kelly got 7, is the smallest score. Bob got 7, Tim got 0, Bob got 7, Tim got 0. So you can see the smallest and the largest. I'll post this code. Yeah, thanks for pointing it out. So it's in the contest sample solutions channel, but maybe a meeting chat would be better. But yeah. So maybe if you want to do one more question, pretty much in the exact same format, but if you want to this doesn't even need counting. It's just checking whether you have a duplicate, but you can do it somewhat the same way, I guess. Okay, so if you want to look at that new question. Does anyone have any questions about the basketball example? Control plus. Okay, if there are no questions, we can work on the other one. I'll just leave this up.
I could talk about this problem because I have the solution ready. So, okay, yeah, let me share my screen first. So this one is another like problem that you can solve with using hash tables. Or in my case, I'm also using C++, so I use the map. So this is technically binary search tree, but either way, it still works this way. So first you just get the input, obviously. So you get like the number of rounds and get like the first word. I used a variable to keep track of which player was currently playing so that I knew which one lost in the loop. And then you also want to keep track of the previous word because the two things you need to check is was the word said before, and then is the word that's currently being used. Does a first letter match the last letter of the previous word? So in the while loop, basically I just said well, actually you could use a for loop because it does give you n, right? And it should be, yeah, n should be the number of rounds. So I don't know why I use the while loop, but you could use a for loop here, but I use the while loop. So while there's inputs, basically, I said like there's two things I'm checking. So what's the word said before? Like I used the map, and then I put the word into the map first. I use the Boolean map. So the key would be the string, which is the word that was said, and then the value would be just a Boolean, like true or false. Was it said basically? I said if it was true, then it would check that track variable and see if player 1 lost or player 2 lost, and then just return. And then if not, then it would put it into the map, put that word into the map as true. And then I check after to see if the front matches, if the front does not match, or if the front of the current word does not match the last character of the last word, then I say, I do the same thing as what I did here. You could switch these up too. You could do this one first and then check if the word was said in the past after. But I just did it this way. And then you just want to update the previous word. And then increment track, I guess, unless you did it, unless you're keeping track of who wins and loses a different way, but I use this variable to keep track of that. And then at the end, I just said fair game. So like, you can see with the two of the test cases that they had there, if I run them, then, I mean, it already shows the result, but they both pass.
Did you try submitting?
Yeah.
Okay.
Yeah, I submitted and this passes.
Yeah, this question you can solve with a map. You can solve it with a string. With the set. Maybe it's worth showing a set solution as well. That you think?
A set solution.
Actually, I think I did this problem a bit back, it seems like, and I have a set solution. So I'll just show that.
Okay.
So I'll space it out. So I have variables p1 loss equals false, p2 loss equals false. And then I have a set of strings, and basically I have a string previous, and I modify the value of previous every time. And then a set of words that have been used already. So I'd insert it into the set. And then here, going from 1 to n, not 0 to n, because I'm already grabbing it once. And then I just do it in one statement. If use.countS, which means this exists in the set. This gets a returns true or false, whether or not the element exists in the set. Or if you've used that word already, or this new word that you get, the previous words, the last character of the previous word, if it's not the first character, then do false, things like that. And then check whose turn it is. So if it's turn 1, then 0 is player 1 or something. So in this case, so from 1 to n-1, if it's an odd number, then it's P2's turn and they'll be losing. And then at the end, I just marked if both players didn't lose, then fair game, and otherwise print out someone lost, something like that. So I'm gonna combine the elements instead of printing in the middle, but it's the exact same thing. And then you can use sets. Set, you would use insert and erase, and you can insert into the set, and then you can count whether it exists in the set. So that's the use of the set here. But it serves the same function as the what Jesse was doing. Yeah. The only thing is you're using like word thought front and back. Did you save the previous value, or did you do like, how did you store it again? Did you like?
Yeah, I saved the previous value in another string.
Okay, yeah.
That's what I did.
So you might want to do that. Yeah. So you could use a set for this. You just need to know whether it's been seen already. So yeah.
Yeah. In this case, it actually makes more sense to use a set. Probably.
But
'cause
the map
you have
just
the
has
value.
more information. You just don't
Yeah.
need all the information necessarily. Yeah. Okay. And then Aaron posted a Python example. So the map would be called a dictionary in Python. So very different. So dictionary has the definition, it has the name, kind of like that. So as long as you have a pair of key value pair, you can have a thing. And so maps, for example, you can actually pair anything with anything. So you can pair a string with the vector and things like that. So you can do some crazy stuff. Yeah.
Yep.
And one like data structure we didn't talk about is like heaps, but heaps, you can build it off of an array, things like that. So yeah, really crazy. But you consider it a different data structure because you have a different, does it get harder from here? Yeah, of course. This is just checking whether it exists in a set, right? But yeah, it's you have a set and then you insert and you yeah.
Yeah,
But
it might be hard to like understand these things when it's your first time hearing about them, probably.
Yeah. The first thing to do is to do loops and conditionals and become more comfortable with that. And then you can start working with like other data structures and things like that and algorithms. But maybe we'll just try to fit in some brute force stuff just because brute force is really important, and just being able to write that super important. So maybe we'll fit in like brute force problems every week or something. That could work. What do you think?
Yeah, we could do more brute force. Or at least like for the problems that we do, we could show brute force solution if there is one
Yeah.
that doesn't involve data structures.
Yeah, I think a good place to start would be like the DA hack coding competition questions, all of them in the qualifying round and the competitive round. Those are all pretty much brute force. So if you can get comfortable with that, you do a lot of different things, but they're all brute force. You just write loops and stuff like that and go through everything in order and do checks, and you have to write out a lot of code. But yeah, you don't have to optimize much, but you do have to write a lot. So it'd be somewhere to start for sure. And yeah. And then moving forward, we're going to be saving everything into this presentation, or maybe like a website or something. And then so you can jump to like input output, you could jump to algorithmic complexity, sorting, data structures, and then should be able to find links to the presentations and things like that. So I need to have this so that you can join at a different time and kind of check it out, and check a recording, something like that. And then we'll have some practice problems as well. So, where that. But yeah. I think that's about it for today. Kind of lower on the active programming side, but that's a lot of information. So we'll be covering that information and focusing on different data structures and kind of reviewing some stuff again. So probably do, so we did some map problems and a map problem and a SAT problem, and maybe can do something else next time, but we're not gonna move on for a few weeks. We'll do a bunch of different data structures, and then we'll get to talking about when to use what in what scenario and which different data structures might work, things like that. And or maybe talk about like language specific stuff, anything. Yeah. Yeah. Probably really confusing to be honest, but yeah. Anyone have any thoughts? Like what do you think this is a decent starting off point to work off of, or what do you think you're confused by? I think like personally, I think maybe the implementation part, like this presentation has no slides whatsoever, right? No like sample code whatsoever. So maybe that'll be something to do, add sample code and add like what are the most generic way of using these things, to show an example of so adding, removing, checking. So I have the examples for arrays, but for everything else there isn't really anything. So were you able to solve the SAT problem? Probably not. I guess you'd have to be familiar with the sets and maps beforehand in order to be successful with that. But
Yeah, maybe we'll do more practice with sets actually, because I feel like they're pretty common in the questions we do, right?
Okay.
So maybe we'll focus on this structure for a while.
Maps and sets. Yeah, we might do maps and sets again. Yeah.
Yeah. I don't really see linked list that much.
Yeah. Kind of specialized. And talked about it briefly, but you can do sets and stack like linked list stuff. You can do stacks and queues with a large enough array or something, or a lot of the time. Yeah, if you have like a big enough array, then you can keep on moving forwards and backwards, and that would actually, yeah. If you're using a different language from the demonstration, yeah. So maybe, yeah, it can have language specific stuff. I think Java especially is easier to conceptualize like the abstract data type versus data structure distinction, because you can do stuff like list of integer is equal to new array list of integer or something, and you can like define it that way where you have the list interface. It's called like an interface in Java, and then you're doing that with the data structure array list, things like that. And you can also do like list is equal to a linked list of integers and things like that. So you can actually type it really in an unambiguous manner by doing that. So I think Java makes a lot of sense in that way. After a while, it's just like a lot of typing, but it's it might be clear to understand. Yeah, we'll also do some priority queue stuff and sorting as well. So yeah, a lot of stuff, but each of these topics you can look up, but these are the basic things that you need to know, I think. So just array, string, linked list, binary search tree, and hash map. And then if you know about these, then I think you have a really solid start. So, and I don't even know much past this. Yeah, I don't know much past this. Like the next data structure is like, I don't know, like segment tree or something, like heap. Heap you can substitute binary search tree. I don't know if you even need anything else until way later. So this is yeah, you just have to combine it in different ways. So okay. Anything more? How about Peter? Haven't said anything today.
Yeah. Didn't have much to say. You very much covered everything, so.
I think
Yeah.
I think that's pretty much it for this meeting. Like,
Okay.
we can
So
start-
moving forward, we'll build off of this and have some practice problems for a lot of different and for a lot of different scenarios, and then start to solve. So yeah. I think that's it for today then.
all right. Gonna stop the recording.